All right, welcome back to Math 676. In this next lecture, I would like to talk about a few strategies how to program in a way that you introduce fewer bugs and that you find them more quickly. So if you think about programming, one of the things that I think I've personally learned over the last 25 years that I've been a programmer is that being a good programmer does not necessarily mean that you introduce or that you make fewer bugs in your programming. That, let's say, when I think about myself, I introduce bugs all the time. And I think what makes me a reasonably decent programmer is that I have developed ways how I can make my programming, let's say, I changed my programming style in such a way that I find bugs more quickly. So in essence, what I try to say is that good programmers have found ways to live with the fact that they introduce bugs, that it's not quite as painful anymore as it is for people who are new to programming, for example. So what I would like to do in this lecture is that I show you a few strategies that we call, for example, defensive programming, that avoid bugs or that make it easier for us to find bugs. And then in the next lecture, I'll show you some more things about how to use a debugger that once you do have a bug and you need to find what exactly it is that's going wrong, that I can demonstrate a few ways how to do this more quickly than, let's say, the traditional way of introducing printf statements just to find out what the value of a variable is and so on and so forth. So this lecture then will be about, let's say, strategies to make programming less error-prone. So the basic premise of this class is that good programmers introduce bugs too. That this is just a fact of life, and that what distinguishes good programmers is essentially just that they have developed ways to fix them more quickly. So as a few observations, when you're a good programmer and you've been programming with a programming language for a long time, one of the things that certainly happens is that you become familiar with the syntax of the language, and that you don't have to do as many round trips where you call the compiler tells you that there's a syntax error, you go back into the editor, you fix it, and you call the compiler again. Certainly when you have a lot of experience in programming, that is something that you get better at. The one thing that even good programmers do is they introduce logic errors. They forget about corner cases, they start at index 1 when they wanted to start at index 0, and so on and so forth. These sort of things just happen. So what good programmers do is they have developed practices to find errors more quickly. And so what I would like to talk about in this class is essentially best practices, things that we have learned that reduce the number of bugs that you have to find, or at least that make it more, let's say, not quite pleasant, but less painful to find bugs. So the first approach that I would like to talk about is something that is called defensive programming. And essentially, the approach of defensive programming is that you start out programming with an understanding that you will make errors, that is a fact of life, and that you observe what kind of errors you make, and that you learn from this, and that you take active precautions in your programming style to avoid them from happening again, or to, let's say, make it more obvious if such a bug happens. So the premise is that there will be errors in your program and that I need to change the way I program. So when I say that there will be bugs in codes, bugs can come in many different ways. For example, let's say when you write a software like deal.II where you provide functionality to others, then what you have to expect is that your users make errors in calling these functions. That, for example, they will access elements of a vector that don't exist. That is something that will happen, whether you want it or not. Similarly, when you write codes for yourself, you also will make errors in your own code. That too will happen. The fact that it happens has a name. It's called Murphy's Law, right? That everything that can happen will eventually happen. And I think that is definitely true for programming as well, that if there's a potential for a bug, if there's a potential for somebody doing something wrong, sooner or later they will do something wrong. So I want to essentially give you a few examples of defensive programming and let's say the approach that we take. And remember that the general strategy was always to assume that a problem will happen, that it's not a question whether it will happen, but that it will happen and that we have to deal with it. So here's an example of a function, for example, that could read a line from standard in from the screen, from the console, where people could enter text and then do something with it. So the C programming language has a function that is called getS, where you give it a buffer that's an array of characters, and it's going to read from the input as many characters until the end of a line. So if you would type something in onto your console, and by the time you hit enter, that's the amount of text that getS reads at one point. And if you want to read multiple lines, you will have to call getS multiple times. So a maybe not uncommon approach, let's say if somebody wanted to enter commands, let's say you're in an interpreted language, would be something like this. So you would create a character buffer, or an array called buffer of, let's say, 1,000 characters, and then you would put this buffer as an argument to this function getS, which reads the input, and then you do something with this buffer. So, of course, the number 1,000 is chosen rather arbitrarily, and you could argue, well, what could possibly go wrong? I mean, nobody would be stupid enough to enter more than 999 characters plus the end line character into one line of input, right? I mean, 1,000 characters must be enough. But the answer is, of course, that, well, sooner or later, somebody is going to actually enter 1,050. And what is going to happen in that case is that this function getS just happily reads 1,050 characters, and it will overwrite this the end of this buffer variable, and whatever is past the end of this buffer will be overwritten. And as a consequence, your program might do whatever. Maybe it's going to reformat your hard drive. So this is the sort of situation where you know that eventually somebody is going to add or to enter more than 1,000 characters. And I should say that this function getS has been long recognized as a problem because it doesn't know anything about the size of the buffer, and it has been deprecated, I think, about 15 years ago. And in the latest incarnation of the C standard in 2011, getS was actually abandoned because it is just a source of continuous trouble. But it illustrates the point that just because you think that nobody is going to be stupid enough to enter more than 1,000 characters does not prevent an error. Somebody eventually will do that. And so the right approach to this would be to call a function that is called fgetS, that is a replacement to getS, which takes this buffer variable here, but where you also have to specify a length of this buffer, 1,000 characters in this case, and in particular you have to pass the variable that describes the input stream, so in this case standard in. So fgetS can produce an error if somebody gives you a line that has more than 1,000 characters, and that would be defensive programming because we anticipate that eventually somebody will enter something that is more than 1,000 characters, and we deal with the situation. We anticipate the problem and we deal with it. A second example would be, let's say in deal.II we have a class FE collection in a namespace called HP. So this FE collection class, essentially we use this in the HP refinement context. You might have different finite elements that you stick into this collection. Think of it as the equivalent of an STD vector. So you could argue that in no finite element program you will ever use more than 256 finite elements. And it is probably true that in no reasonable finite element program you will ever use more than 256 different finite elements. So maybe we should do the following. So we should return from this function, if you ask for the number of elements in this collection, a variable of type byte that I have type diffed to an 8-bit integer here. So the maximum number that this type byte can store is 256. and we should just ask this collection, which could be an std vector, for example, for its size. We will convert the size to byte because we know that no reasonable program will have more than 256 elements, and then we return that. Of course, the problem is Murphy's law tells us at one point somebody is going to use more than 256 elements, and in that case, let's say somebody has 258 elements, the return value in this case would be a byte with a value of 2. And so this is again a case where it's just really awkward to deal with the consequences of this. It would be much better if we guard against this sort of possibility. So, I mean, one way would be to return an integer, but if we insist on returning a byte, for example, we should at least make sure that the value that is being returned is reasonable. So we should add an assertion here, for example, that checks whether indeed the size that this collection returns, that this member variable returns, is less than the maximum value that can be stored in a byte. That is something that we can get from this class numeric limits that the C++ standard provides for us. So if in almost all cases the number is indeed less than 256, everything is going to be fine. If it is more, then at least the assertion triggers. A third example that I've shown you in a previous lecture already is if you access the elements of a vector, then you could of course say, well, if the vector has 10 elements, why would anybody access element 15? But Murphy's law says that that will happen at one point or another. Somebody will access element 15. And so if we just return the 15th element of a vector of length 10, then that will be a nonsensical value. And so you can, of course, write this sort of code, but it's going to be very difficult to find out what exactly it is wrong in your code if you allow access to the 15th element, because all that's going to happen is that your program produces unpredictable, wrong, maybe not quite obviously wrong results. It would be much easier if we just anticipated that these sort of errors happen and guard against it. That's defensive programming. So the approach would be that we have an assertion that makes sure that the index that we are accessing here is indeed less than the size of this vector. So a summary of this approach essentially would go like this, that poor programmers think that they're good enough not to make errors, or that if they do produce errors, that they know how to debug them. And what they don't realize is that, well, of course we make errors. Good programmers know that they make errors, and they have learned that it is painful to deal with errors if you have to just deal with the fact that your program produces something that is wrong, for example. It is far easier to write code in such a way that it anticipates that we make errors, and so we expect that bugs happen, and then that we catch them. So, for example, that we add assertions. That is far easier than having to debug your program. This is not an inherent trait in good programmers. This is something that I think a lot of us just have learned from experience, that over the years we have learned that we make errors and what kind of errors we make, and that we guard against this. So this is something that I really want to impart on you as part of this lecture, that you can change the style of programming and you will realize that you will find bugs so much easier than if you just wait for bad things to happen, and then at the end of the program run you get results that don't look correct, but it's not quite clear where exactly it was that something went wrong. So this is what we call defensive programming. This is something that we definitely practice in deal.II, where we have a lot of these assertions, for example, where the people who program this have learned that they need to anticipate bugs and change the behavior. That is, I think, what characterizes good programmers, that they anticipate that they will make bugs, that they know that they will make bugs. So here's a corollary to this. When you have, for example, a check in your code that verifies that, let's say, you only access valid elements of a vector, then you have two choices. Either you could, for example, print an error on the screen, or you could abort the program. And I think an experienced programmer will always opt for the option to abort the program. Because if you just print the error, then you will possibly get one line on your screen among many other lines that your program produces in the output. Whereas if you abort the program, then, well, definitely you will get notified about it, right? The program in that case will stop, and you know that something went wrong. The point of aborting a program is that, well, what good can happen after you have accessed element 15 of a vector of length 10? There is nothing useful that can happen at that point. There is no point in printing an error on the screen and then continuing to do something. So if you find that something has gone wrong in your program, abort the program. It also makes it a lot easier to debug it, and I will show you this in the next lecture, how much easier it is when you abort the program, because then the debugger will stop right at that place, and you can inspect the, let's say, local variables that you have at that point. A second corollary to this is that one way to write checks that abort a program will be to use assertions, and I've shown them to you in a previous lecture, because they simply abort the program. But the other thing that I want to say is there can never be enough assertions. If your code has 100 assertions in 1,000 lines, that's wonderful. So you shouldn't think that there is an upper limit of how many assertions you should have. Every assertion you have will eventually help you find a bug, and so the more you have, the easier it is going to be for you to produce a code that actually does what it's supposed to do. So in addition to these defensive programming strategies, I would like to give you 6 or 7 more ways how, let's say, we have learned to avoid bugs. So defensive programming is not about avoiding bugs. It is changing your behavior because you know that there will be bugs. Here's a few ways how to avoid bugs to begin with. So the first approach is something that is typically called design by contract. Essentially what this means is that instead of barging right into writing your code, you first sit down and you essentially write a specification of what a function or a class does. So you would, in the specification, not describe exactly what algorithm a function does, but you would write, well, if this is the input, then that should be the output. And that should cover corner cases. So for example, you would, let's say you have a function that splits text into lines that have no more than 80 characters, because you want to print this on the terminal. Then one of the things that you would have to think about, let's say when you try to specify this, is, well, if the input has already new lines, what would that mean for the output? Or if the input happens to be the empty string, what would that mean for the output? So in your specification, you would specify what's going to happen in these sort of cases. And once you have the specification, then you start writing the code. The reason why this works is because oftentimes when we start to write code, we actually only have a relatively vague idea of what exactly we want to do. So if you have only a relatively vague idea and you start to program, and then you realize, oh, I didn't cover this corner case here, I really need to think about this, then oftentimes you need to go back and you need to revise the algorithm that you already wrote. Revising functions and revising code is a common source of errors, because you didn't anticipate something in 3 different places, but later on you fix it in only 2. If you had anticipated this before you even started programming, you would have gotten it right in all 3. So design by contract is one way how you can avoid mistakes, because you first have to think about it and then you code it. A second approach would be to use what's called coding conventions. So coding conventions essentially say we should have a common way to name functions. We should have a common way to do things. We should, if we have functions that return a number, they should always start with n underscore, for example. And the point is that it makes it easier to remember things. And if you remember things, then that avoids errors. So let me give you an example for this. In deal.II, we have a function where you can give it 2 triangulations, and it produces a third one that consists of the union of the cells of these 2. So let's say I want to have an operation of the kind that my object tria3 is the union of these first 2. The function that does this is called grid generator : merge triangulations. And the question is, the argument list be try 1, try 2, try 3 if this is the operation that I want, or should it be try 3, try 1, try 2? The answer in this case is that it's the former, because in deal.II we have a convention that says that among function arguments, the first few are always the input arguments, and the last few are the output arguments. So it's obvious that it needs to be the first one. I don't need to even look it up in the documentation of this function. It must be like this. I should also say there are a few exceptions to this. But by and large, this is the convention that we follow. And it makes it easier for us to write code without bugs because we don't have to think about this. We don't have to look it up. We cannot forget which of the two approaches would be correct. A third way would be if a function or if a variable is const. The same is true for member functions. But if a variable is const, mark it as const, because it helps you when you read your code, you understand that there is no other place where you could change the value of this, and it allows the compiler to help you. So here's an example. Let's say if we want to compute an error, one of the things we have to do is we need to loop over all the cells, and then on every cell we need to loop over all of the neighbors. So let me introduce a variable that is called nNeighbors. So this function nActiveNeighbors doesn't actually exist. It's just a mock-up here. But the idea is, let's say I call this function once, I assign it to a variable, and of course for every cell that's a constant number. It's not going to change throughout the rest of this loop over all the cells. So I might as well make it const. Why does that help us? So the first thing is that when I read this declaration, I know that in the other 50 lines of code that are in between here before I use this variable, it cannot possibly be changed. I don't even need to read this. I know it's been initialized once, it will not have changed. I don't need to find out if there are other places. But then also, for example, here I'm asking if nNeighbors equals 0. The compiler will tell me you can't do this. Because what I'm actually trying to do here, of course, if I write just one equal sign, is that I try to assign 0 to nNeighbors. That's not what I wanted. It's legal, C++ syntax. What I really wanted to do, of course, is ask if nNeighbors equals 0. So because I've marked this variable as const, the compiler can tell me you can't do this, and it helps me spot an error that might have been difficult to find otherwise. A fourth approach would be to limit the scope of variables. So in C, you would have to declare all the variables at the top of a function. And a lot of programmers still do this. I think it's actually a terrible practice. I think that what we should really do is declare variables right at the first place where we need it and let it go out of scope immediately after the last place where we use it. So here's an example of why this is the old style of doing it, where you declare these variables at the top of the function, is a poor way of doing things. So let's say, for example, I have a function where I need 3 indices, idx1, idx2, idx3. And then I use them further down the line here. So there are 2 bugs in this thing. The first thing is, well, I'm trying to compute a sum over all the elements of a vector. And I have this loop here. And then at a later point, I want to compute a partial sum, for example. And I have simply copied this loop header. But what I've forgotten is that I need to not just increment or not just check idx3 here, but that I also need to increment idx3. So that's definitely a bug here. As a matter of fact, this is an infinite loop that I have here. Then similarly, I have forgotten that I should also use idx3 in this particular place here. So these are two definite bugs. There are 2 possible bugs as well. Namely, I might have so I initialized idx2 and idx3 in these 2 places here, but maybe I have already used them in this code in between here. So maybe they are not at the value anymore that I expect, or maybe that I had at the time when I wrote the code initially. So these are 2 possible bugs. A better approach would be to declare these 2 variables right in the loop. Because then, for example, idx2 goes out of scope at the end of this loop, and this here is a syntax error. The compiler can tell me this because idx2 doesn't exist in this loop anymore. Similarly, down here. So you see that declaring variables only in the scope where I actually use them helps you avoid errors and helps the compiler help you. Properly indenting code is also something. So I see this a lot with my students that they don't care about indentation, and I think it's a bad habit. Let me show you an example here. So let's say if I have this function here. I have a nested condition if, another if here, and then I've copied some code from somewhere else. And I've copied it with the indentation that was the case over there. So it doesn't match the indentation. And I mean, maybe you think that you can read it, but one of the questions that you might have is, well, which else does this actually correspond to? You might think that this actually corresponds to the first one because it's roughly aligned, but that's not true. The else actually corresponds to this one here. And it would have been much easier if you actually indented it properly, because then it would be obvious to see which this else corresponds to. So that's why IDEs like Eclipse, for example, have a function to indent a block of code. Use that. It makes it easier to read your code. It makes it easier for you to avoid errors. Second to last, listen to your compiler. So when you have, when your compiler produces warnings, take them seriously. Not every warning that it tells you about indicates that something really bad is going to happen. But sometimes it does. And you don't want to be in a position where the warning indicates a serious problem, but you don't see the warning because you have ignored the other 10 warnings that have accumulated over the last week of programming. So make sure that when you compile your code, it doesn't show any warnings at all. It's a way for you to ensure that you can let the compiler help you. So an example, deal.II is written for no warnings at all. And the last one is, of course, when you write code, you need to test it. That is something that maybe I'll come back at a different lecture, because that is a very, let's say, it requires a little bit of infrastructure. But it really helps you avoid bugs if you write dedicated tests for whatever you do. Beyond this, there are many tools that you can use. So, for example, what I'm going to show you in the next lecture is that you can use a debugger. Then there are other tools like Valgrind's memcheck or a massive cache grind call grind. These are tools that help you find bugs in your code. And you should learn to use them because they help you find bugs. As I say, some of these will be covered in future lectures. So I hope this gives you a little bit of an insight of how to become a better programmer, how to avoid mistakes, and how to, let's say, structure your code in such a way that either you find bugs more quickly or that you don't produce these bugs in the first place. As I said, in the next lecture, I'll show you what you can do if you actually have a bug and you need to find it, and we'll come back to that in lecture 25.